On the eve of Christmas 2024, NASA's Parker Solar Probe, traveling at a staggering 430,000 miles per hour, ventured into the most perilous realm of our solar system. As the world celebrated, the probe plunged within just 3.8 million miles of the Sun's surface, equivalent to standing a mere half-inch from a raging bonfire the size of 1,000,000 Earths. This was no ordinary solar flyby. Parker was penetrating the Sun's very atmosphere, capturing images and data that no human eyes had ever seen before. This mission was not just about exploring the Sun's surface, but delving into the chaotic stream of material blasting away from it. The solar wind, in its infancy, was a torrent of charged particles carrying the Sun's magnetic field across the solar system. Normally, by the time this wind reaches Earth, it has been smoothed and stretched by millions of miles of travel. But here, Parker caught it raw, turbulent, and violent. Among the most striking features were 3 massive coronal mass ejections, CMEs, erupting in quick succession. CMEs are already among the most powerful explosions in the solar system, but Parker's AI analysis revealed something unprecedented. These 3 didn't just pass each other in space. They collided and merged into a single monstrous wave of plasma and magnetic energy, a cannibal CME. Such events, rare though they are, can supercharge the solar storm's effects, turning a normal geomagnetic disturbance into a planet-wide event capable of disrupting satellites, crippling power grids, and altering the ionosphere in ways we barely understand. While most of the attention fell on the CMEs, Parker's images also captured the heliosphere at the current sheet in astonishing detail. Imagine a vast, spiraling ballerina's skirt of magnetism stretching billions of miles from the Sun, wrapping around the planets and shaping the very architecture of the solar wind. This current sheet isn't static. It's in constant motion, twisting and warping as the Sun's magnetic poles reverse over the 11-year solar cycle. AI-assisted modeling of Parker's images revealed ripples and folds in the sheet that appear to influence the paths of CMEs, funneling some directly toward Earth, while deflecting others into deep space. This discovery could revolutionize space weather forecasting. By tracking how the current sheet shifts in real time, scientists might one day predict not just when a solar storm will hit Earth, but exactly how it will strike and how severe its effects will be. Back in 2018, Parker first detected the strange switchbacks in the solar wind, sudden zigzags in the Sun's magnetic field that seemed to whip the plasma back on itself at incredible speeds. At first, these were thought to be rare anomalies, but the December 2024 flyby told a different story. The switchbacks were everywhere, clustered, intensified, and more sharply defined than ever before. The AI analysis linked these switchbacks to bursts of magnetic reconnection, violent events where magnetic field lines snap, reconnect, and release massive amounts of energy. This could be the long-sought answer to one of the Sun's greatest mysteries: why the corona is hundreds of times hotter than its surface. If switchbacks are indeed conduits for energy transfer, they may be the mechanism by which heat is pumped outward from the Sun's interior, superheating its atmosphere and powering the solar wind. To survive its plunge into the corona, Parker relied on one of the most advanced heat shields ever built, a carbon composite barrier capable of withstanding temperatures over 2,600 degrees Fahrenheit, 1,400 degrees Celsius. The shield kept its instruments at near-room temperature even as the spacecraft hurtled through plasma hot enough to vaporize metal in seconds. But the December encounter pushed Parker to its limits, with radiation levels and particle impacts far exceeding initial mission projections. The data from this pass was so rich and the conditions so extreme that scientists are now re-evaluating how far Parker can safely go in its remaining orbits before the mission ends in 2026. the AI-assisted processing has made one thing clear. The closer Parker gets, the stranger and more dynamic the sun becomes, revealing phenomena that were invisible from afar. This is not just a mission of endurance, it's a race against time, heat, and radiation to uncover the sun's deepest secrets before Parker succumbs to the very star it was sent to study. As Parker's instruments mapped the chaotic flow of particles blasting outward from the sun, the AI identified something entirely unexpected, an immense elongated void in the solar wind. This shadow corridor stretched for millions of miles and had almost no charged particles passing through it. It was not a random gap. Its edges were sharply defined, and it appeared directly downstream of the cannibal CME Parker had observed earlier. The AI simulation suggested that this void was created when the massive CME plowed through the solar wind like a cosmic snowplow, sweeping particles aside and leaving behind a vacuum-like channel. The concern among researchers was immediate. If such a corridor ever intersected Earth's orbit, it could temporarily weaken the planet's magnetosphere, leaving our technology and even biological life more exposed to cosmic radiation than ever before. Buried deep within Parker's magnetic field readings, the AI uncovered a faint but consistent oscillation. This magnetic heartbeat had never been recorded before and seemed to originate from deep within the sun's convective zone. More intriguingly, the pulse appeared across multiple instruments simultaneously, in the magnetic field data, in particle velocity shifts, and even in faint fluctuations in extreme ultraviolet light. Some scientists believe this pulse could be linked to the underlying processes that drive the sun's 11-year cycle of activity. If so, it might one day serve as an early warning system for solar storms, months before they erupt. But the fact that it has only been detected so close to the sun raises an unsettling question. Has this pulse always been there, hidden from us? Or is it a sign that the sun's internal dynamics are changing in ways we don't yet understand? One of Parker's last high-resolution sequences focused on a vast filament of plasma suspended above the sun's surface. These filaments are common, but this one was different. It spanned nearly 2 million kilometers and appeared unstable in ways that the AI flagged as high risk. Magnetic field mapping revealed that its anchoring points were weakening, and the surrounding magnetic loops were shifting rapidly. If such a filament were to collapse and erupt while facing Earth, it could unleash a coronal mass ejection with enough energy to rival the infamous Carrington event of 1859, a storm so intense it set telegraph wires ablaze and lit up the skies with auroras as far south as the Caribbean. In today's world of satellites, power grids, and global communications, such an event could cause damage on a scale never before experienced. Perhaps the most baffling discovery came not from Parker's images, but from its radio telemetry. As the probe skimmed the edge of the corona, it detected a narrow band, repeating signal that didn't match any known emission pattern from the sun. The AI confirmed it was not an artifact of the spacecraft's systems or an echo from Earth. The signal originated from the surrounding plasma itself and pulsed in a structured, non-random pattern. While most researchers lean toward a natural explanation, perhaps a previously unknown plasma resonance, its precision and timing raised eyebrows. Some quietly speculated that Parker had stumbled into a phenomenon that might point to interactions in the solar plasma we have never imagined, or worse, a process that could influence the very behavior of the solar wind on a large scale. The Parker Solar Probe's mission was never meant to be easy. It was meant to be historic. Its purpose was to fly closer to the sun than any human creation had ever dared to uncover the mechanics of our star's atmosphere and to help us prepare for the storms it sends across the solar system. But what it delivered in its final encounters was something far more profound, a glimpse of a sun that is stranger, more dynamic, and perhaps more dangerous than we had ever imagined. The cannibal CMEs merging into a single superstorm, the vast shadow corridor carved into the solar wind, the rhythmic magnetic heartbeat deep within the sun, the unstable filament poised to unleash devastation, and the mysterious signal from the corona. All of it paints a picture of a star that is alive in ways we're only beginning to understand. These are not just random anomalies. They are pieces of a larger puzzle that could hold the key to predicting and surviving the most extreme space weather events our planet might face. For decades, we've treated the sun as a constant, a dependable source of light and heat. Parker has shown us that beneath that familiar glow lies a restless giant, capable of reshaping our skies, disrupting our technology, and even altering the habitability of Earth if its fury ever truly turned our way. And perhaps the most haunting part is that we might now have the tools to see it coming, but only if we understand the signs in time. As Parker's journey draws to its inevitable end, it leaves behind a legacy not just of data, but of warning. The sun's power is absolute in our solar system, and while it has sustained life on Earth for billions of years, it is a force we can never control, only respect, study, and hope to predict. And now, with the probe's final transmissions echoing back across the void, we are left with a chilling thought. What if Parker's last gift to humanity was not just knowledge, but a countdown